Well, I hope the sound of this video is going to be better and I'll try not to mumble anymore so that it's clear on what I am saying and what I need you to do. Today, we're talking about dynamics of uniform circular motion. So we know already that dynamics means it involves forces. And we know that according to Newton's second law of motion, an object that's experiencing acceleration, so accelerating, it must have a net force acting on it. So we have an object, there is velocity, we figured out acceleration last time, and then there will be a force acting on it. So the force that we call radial force, radial component, is going to be equal m(a)r, and we know that ar is v squared over the radius. So here is our formula for the force for the circular motion. On this diagram, we see that the force is directed towards the center of the circle. Why is that so? Because we know that the acceleration is directed towards the center, so the force also has to be directed towards the center of the circle. And there is not much else to say here. So we're going to dive in straight into the example. So our example is about force on revolving ball, which is spinned horizontally. So you just imagine you're spinning it, it spins horizontally. So estimate the force a person must exert on a string attached to a 0.150 kilogram ball to make the ball revolve in a horizontal circle of radius 0.600 meters. The ball makes 2 revolutions per second, which means that t time is 0.5. We did that last time in the example 5.1, and we are going to ignore the string's mass. So we are going to apply our Newton's second law. So we're going to say that the sum of the forces is going to be equal m(a)r, right? And then we know that AR is V squared over R. We just wrote it down. And we also know that V, the velocity, is 2 pi R over capital T, pi R over capital T. So we can immediately calculate the velocity here. So it's 2 pi. The radius that's given to us is 0.6 meters, and we have to divide it by half a second, 0.500 seconds. So that is going to give us 7.54 meters per second. And now we're ready to plug in the velocity into our formula for the force. So Fr is going to be equal, or tension, we can call it Ft. Actually, I'm going to call it T, because estimate the force that a person must exert on a string attached. So the tension is going to be mass, which is 0.150 kilograms, times v squared, which is 754 meters per second squared, and divide by the radius, which is 0.600 meters. Once we do all the calculations, we should get approximately 14 newtons. So that is our answer for this problem, and we are going to look at some similar problems over here. I'm going to scroll down to example 5.4. I'm actually going to have you do those problems, so I'm actually going to say it here in case it is not clear what I'm saying. I'm gonna write it down. Try it yourself, and I am going to give you the answer, so you can pause this, and then I will give you the answer so that you can check it. So pause, do this problem yourselves, and then the answer is going to be the force. Okay, so for part A, hold on. Sorry, I lost my answers. So velocity is going to be, for part A, is approximately 3.28 meters per second, and then the force is going to be 735 newtons. That is part B, if you solve it correctly. All right, and then another example that I have here is checking how well do you understand the concept. So it's about the tether ball, And the question is the following. After the ball is struck, it revolves around the pole as shown on this diagram. In what direction is the acceleration of the ball, and what force causes the acceleration assuming constant speed? So that's the question. I'm going to leave you with that, and that's it for today.